How much force is necessary to stretch a spring 0.25 meter when the spring constant is 95 Newton per meter? So first you write the given value. Here stretch. So extension or the stretch is 0.25 meter. X value is given. Spring constant K 95 Newton per meter. How much force is necessary? So we have to find the force. And we should write the formula. K is equal to force over extension. And the force is equal to K multiplied by extension. K value is 95. X value 0.25. Multiply the values and write the unit Newton. So you can write the answer here with the unit Newton. Question number 2. A spring has a spring constant 56 Newton per meter. Spring constant K is equal to 56 Newton per meter. How far will it stretch? So we have to find the extension. When a block weighing 18 Newton, so force is given 18 Newton, is hung from its end. X you have to find. You know the formula, K is equal to F over X. So X is equal to force over spring constant. Make X as a subject. Now you substitute the value. The force 18 and spring constant 56 and divide it, and your unit must be meter because the spring constant is given in meter. So your extension will be in meter. Question number 3. A spring with a spring constant of 144 Newton per meter. So K 144 Newton per meter is compressed by a distance of 16.5 centimeters. So the extension, compression, extension is the same. So 16.5 centimeter. Okay. If you compress the spring, it stores potential energy, and extend the spring also, it will store the potential energy. How much elastic potential energy? So U question mark. What is the formula? U is equal to half K X square. Half K value 144 spring constant is given, and this we need a conversion here, because if you notice Newton per meter and here is centimeter, so it contradicts. So change this centimeter to meter. 16.5 divided by 100, 0.165 meter. So 0.165 meter, and square is here, and many students they forget to put the square. Don't forget, and then calculate using your calculator. Unit is joules. Okay, so question number 3 is done. And question number 4. A spring has a spring constant of 256 K 256 Newton per meter. Note the extension must be in meter. How far must it be stretched? So we have to find the stretch or compress is X. We have to find X to give the elastic potential energy 48 joule. So write the elastic potential energy formula, half K X square. Now make X as a subject. So how can you make half k x square is equal to u, and I don't want this half, so I write here 2 and here 2. So this cancel. I don't want this k here and k here. Cancel this. And I don't want this square. So remove this and put the square root. So x is equal to square root 2u by k. Now you fuse the value. Given values u 48 and k 256. Use your calculator and find the answer in meter. That's the answer for 4. So it is done. Now the next question, fifth question. Two springs look alike but have different spring constant. We have two springs and it looks alike, but k values are different. Different k values. How could you determine which one has the greater spring constant? Okay, suppose, imagine this has the greater, like 10, and this has 5. So what is the difference if the spring has a greater spring constant, which needs more force to stretch, which is harder spring? Okay, so we can find it by stretching. So you can write answer by stretching or by adding loads, by adding equal loads, and find the extension. Question number 6. Objects of various weights are hung from a rubber band that is suspended from a hook. The weights of the objects are plotted on a graph against the stretch of the rubber band. How can you tell from the graph whether or not the rubber band obeys Hooke's law? Okay. Now they say there is a graph and they are adding the weights and they are calculating or measuring the extension and they are plotting the graph. And if the graph creates or makes a straight line, then the material obeys Hooke's law. Because the Hooke's law says the force is directly proportional to the extension. If you add 1 Newton, the extension is 2 centimeter. If you add another 1 Newton, the extension is 4 centimeter. And you add one more force, the equal one more force, and it is 6 centimeter. So as the force is increasing, extension also increases. Using these informations, now when we draw a graph, now here is the weight in the x-axis, or you can write load, okay, or mass, and here extension or compression, whatever, and write with the unit is here is centimeter and here is Newton, and it starts from 0, 1 Newton, 2 Newton, 3 Newton, and here you can write 2 centimeter, 4 centimeter, 6 centimeter. So when there is no force, no extension, we should know that 0 Newton, 0 centimeter. So the graph starts from the origin, and 1 Newton, 2 centimeter. Here is a point, 2 Newton, 4 centimeter, and 3 Newton, 6 centimeter. Then you connect all these points and it makes a straight line, and it obeys Hooke's law, because as I told, applied force is directly proportional to the extension. Okay, directly proportional means it should start from the origin. The graph line start from the origin and a straight line. Okay, these two factors should be satisfied. Origin, start from the origin, and a straight line, then it is directly proportional. Okay, so you can write the answer like this. The line starts from the origin and the line is straight. Question number 7. How is uniform circular motion similar to simple harmonic motion, and how are they different? Circular motion, if any object is moving in a circular path and it is moving through the same path, okay, and it takes the same path and again. Simple harmonic motion, now here is a spring. When you pull the spring moves up and down, to and fro motion through the same path. So that is the similarity. And what is the difference? Here the force is not directly proportional to the extension, and in the simple harmonic motion the restoring force is acting on an object and it pulls the object always to the equilibrium point, and it is directly proportional to the extension. This point is very important for simple harmonic motion. So which makes difference from the circular motion or periodic motion. Okay, periodic motion means the object is moving through the same path again and again. Okay, and the time taken for one complete circle or one complete rotation, one complete oscillation, this all periodic motion. But simple harmonic motion, we have the time period, and one extra point is very important point which makes a difference is the restoring force is acting on an object and it pulls the object back to the equilibrium position or the mean position or the rest position, and it is directly proportional to the restoring force is directly proportional to the extension. We have tried these. And question number 8, how must the length of the pendulum be changed to double its period? Now we have a length of the pendulum here, and imagine the time period is 1 second. Now the question, how must the length of the pendulum be changed to double its period? So you know the concept, if you increase the length, the time period also increases. It is directly proportional. The time period is directly proportional to the length. Write the formula, time period is equal to 2 pi square root L by G. Okay. So how must the length of the pendulum be changed to double its period? So we want another one formula, because this 1 second you can take as T1, the 2 seconds you can take as T2. So you can write T1 is equal to 2 pi L1G. G is constant because we are doing the experiment in the same place. T2 is equal to 2 pi square root of L2 by G. Okay. Now you can say that the T1 is the reference. Okay. The reference that we have taken as a reference. And now we are going to find what is the time. Sorry, that if you double the time period is doubled, what is the length? Okay, if the time period is doubled, what would be the length of the pendulum? So you will be dividing T2 by T1, and T2 is 2 pi square root of